Okay, welcome to Central Piedmont Community College's Cybercrime Technology Program Distributed Processing course. And in this first block, we're going to try to wrap our heads around distributed processing a bit, just what it means and what it can do for us. Now, in the way of introductions, you're watching this, of course, in an online format for the lecture portion. The lab portion of this course will be in person. But when we get to the lab, we'll introduce ourselves properly if there's anyone new, but most of the time these are, you guys are established cybercrime students for Central Piedmont, so we won't worry much about that right now. As far as course paperwork goes and payment, it should have been handled before we get to this point. By the time you're enrolled in the Moodle shell, that should have been taken care of. Most of these run in a scholarship format right now. Later they'll probably move to a pay format. The plan for this module is you're going to review the online Moodle materials before you come to class, before you come to lab I should say, and go over all the different pieces. There's a lot of background you need before you get into just jumping into the lab to handle distributed processing, so you really need to watch all these presentations and get familiar with some of these concepts before we try them in the lab if you really want to understand what we're doing, because we're going to move kind of fast once we're in the lab. Won't have a whole lot of time to explain the little details about why we may be doing this or that or something else. So please make sure you do your required online work prior to coming to class or to the lab. Successful completion of the distributed processing class means we can give you curriculum credit for CCT 242 hardware data recovery. So if you complete this successfully, you'll of course get that credit, and we'll talk more in detail about that when we get to the lab. Okay, let's get right into it. What is distributed processing? According to Access Data, and you need to get the guide and the hyperlink there and read through that guide. Distributed processing is a functionality that exists within the FTK3 application framework that allows users to create a distributed processing cluster with up to 4 total nodes. And what that means is one computer acts as what we call the header, 3 act as workers, although all 4 work on the processing of the case. So in other words, instead of processing the case on one computer, it allows you to pull in other computers to help it do the processing. As you know, if you've gotten to this point, processing a case can be very time consuming, and this allows us to split that functionality out and remove the bottlenecks that are present with one system and spread it across many systems. So basically, it's a many-to-one kind of a thing. What's the point of it? Why does it matter? Well, if you've processed any number of large drives, you'll understand why this matters. Now, in our courses, sometimes, for speed, we keep the images very small. They're academic images of a few megabytes long or this type of thing. And the processing time on our academic images is hardly ever more than about 15 minutes. So, you may be getting the notion, if you haven't done a lot of full-size drives, like unless you've taken CCT 289 or something like that, you may be getting the notion that, hey, this all happens really quick, this processing stuff. And I'm going to tell you, it doesn't happen very quick, actually. It's actually something that takes a long, long time. Imaging 1 and 2 terabyte drives, which are very common now, can take many, many hours, and after imaging it, you then have to process it. Sometimes those processing those drives can take more than a day, maybe 2 days, maybe a week, depending on how many artifacts are on the drive, and that takes a lot of time, especially if you need to get to something really quick. Now, 3 terabyte drives are on the horizon. There's even larger drives and other arrangements that are coming about. We're a media-driven society. There's no question about that. They're large multimedia files are on every drive now. They're really getting large, and because of that, there's a lot of artifact counts. Over 1 million artifacts on a drive is fairly common. The processing time for that increases very rapidly. It's a very large endeavor and database-driven effort to do that kind of processing. It takes multiple hours and sometimes days to process drives like this. Distributed processing allows us to split that workload over multiple systems. And because we're splitting it over multiple systems, we're able to prevent bottlenecks from ever occurring. So sometimes adding a second system, the speed increase is not 2 to 1. It's actually a little more than that because we're removing the bottlenecks and allowing each machine to bring more of its power to bear. So you actually get a synergistic effect as you add these worker machines and you offload these bottlenecks. And we'll discuss that more as we get on into this discussion a little bit. One of the things we had been doing to counter the processing time problem of increasing drive sizes and artifacts is to build better systems. And that's okay. You can do that. You can always get a better processor. You can always bump up the RAM. You can always get a solid state drive or spend a little bit more money on a faster spinning mass drive or a better front side bus or just a better system in general, or maybe try to offload some power to the GPUs or there's different kinds of things we can do to try to counter this processing time. But the fact of the matter is the processing still takes too long if we rely on a single machine. And when we rely on single machines, there's always the chance for bottlenecks to occur. If we can distribute this workload over many machines, we will have to we're able to then make sure the bottleneck doesn't occur on any one machine. That allows us to be a lot more efficient, allows us to be a lot more intelligent in the way we spread our bottlenecks across the network. So the bottom line is, rather than trying to continually beef up a single machine and keep trying to make it more and more powerful, which of course we want powerful machines even in distributed processing, but instead of chasing a ridiculously spec'd and expensive single machine, we can actually take moderately priced multiple machines and put them to bear on this problem at the same time, and that allows us to be very efficient. And it keeps the gear at an even distribution level, provides us a way of cascading our systems. If we have older systems, we can cascade them down to worker computers, and we'll explain what that means a little more later. But it allows us to spend less money and gain the same level of performance by using distributed processing. That's really the name of the game here, and we'll see more about it as we go. How distributed processing helps? Well, it's the same as it comes right down to being a little gun versus the big gun. A single machine we can liken it to a small gun, and when we put 4 machines at it and then offload our database server to another machine and offload our evidence server to another machine and offload our cases folders to another machine, all of a sudden the synergy builds, and it's not like we have 8 machines, it's like we have 32 machines. It really ramps up the performance in a synergistic effect. And what we have here, we have the little Uzi versus the Gal 8 30mm on the A10. I'm being an old aviator, I can't help it, so pardon the picture. So how does it help? Well, it makes us faster. That's the bottom line, and not just a little faster, typically a lot faster, and we'll see some data on that as we move a little further. It also allows us to be more stable and reliable. You'll find as you get very high artifact case counts or count cases, you'll find that after a few days it's not unusual for a machine to crash because the case is so large, and you don't know it's going to crash until 3 days in. That's terrible. And then you got to restart and hope that 3 days later it doesn't crash again. Distributed processing helps you avoid this type of thing, and you know your results generally within a much shorter period of time. And if there's an issue, you can reset and try again. It's more efficient. You're able to use your hardware more efficiently. You're able to have a migration cycle on the hardware. Your highest end hardware can be your FTK header, which we'll talk about later. Your Oracle server, which we'll talk about later. It can be used for those types of things. You can, in other words, you can have high-end systems, medium systems, low systems, and you can work them through a life cycle. The high-end systems like I said, FTK header or Oracle or something. Your middle systems, might be an evidence server, or might be might be one of your workers, and your low-end systems might be your hold your case folder, or might be one of the workers. It gives you a chance to use that hardware more efficiently if you're hardware constrained. Some basics, just a real quick example here of some real-world results. We have a small case, we call it SLU, and the SLU case has, I forget how large the image file actually is and how many artifacts, but the bottom line is this: on a Fred system, which is a 32-bit XP machine on a quad-core processor running FTK3, it took about 4 hours to process the case. I want to say it was around 500,000 artifacts, something in that neighborhood. When we ran the same test on the Barneys in our lab, which are 8-core, 8-gig Velociraptor systems, which are in 64-bit Windows 7, we did the same performance in 94 minutes, which is a lot better than a Fred, of course. An hour and half, a little bit more than an hour and a half versus 4 hours. That's the difference between good hardware and medium hardware. But when we process it in a distributed processing fashion, bring 4 machines to bear on it, we get it done in 44 minutes, which of course is a great deal faster than the Fred alone. Not a whole lot faster than the Barney, a little more than 2 times as fast, but we're tying up a lot more hardware doing that. So in that case, in very small cases, the real world results from distributed processing don't really come in that high, but they're still pretty good. But that's a small case. On a medium-sized case, you start to see a little more difference here. This is a little more than 1 million artifacts on the test for safe boot image. It's just a test image we use in the lab. And on that image, when we perform the processing duties of FTK on the Fred, we come in around 20 hours. When we try that same test on the Barney, which again is an 8-core machine with 8 gig of RAM and a spinning mass Velociraptor hard drive, we come in at about 7 hours and 53 minutes. Of course, much better than the Fred, but still 8 hours is a long time to wait on the results. When we perform this test in distributed processing, we get it done in 1 hour and 13 minutes. As you can see, that's a big difference between even the Barney at 7 hours and 53 minutes. That's a big gain of efficiency. Instead of waiting a day on your results, you're waiting an hour, and you can get right to work on your case. And if there's an issue, you can restart it again, and you can still be done well within the time limits of just doing it with one Barney. On a large case, it even gets more dramatic. The larger the case, the more effective distributed processing becomes as we remove those bottlenecks. We have a large case, and what we did is we crammed together a few images. We have some images, HTI-001, Test for Safe Boot, and another one called Test-001. We crammed those 3 images together into the case, and together those are multiple million artifacts. I think 2 to 3 million artifacts here maybe. And the results on the Fred were after about 75 to 100 hours, we generally crash. In fact, we don't generally crash, we always crash. We've done that test multiple times on both of our Freds, and they crash after about the 3 to 4 day point. The Barney on its own gets it done in 28 hours on average, plus or minus just a little bit, but it gets it done in a little more than a day. In distributed processing, we get it done in 3 hours. That is a fairly significant difference. That's around a 9 to 1 advantage, plus or minus a little. That's significant. And if as these drives data sets are getting larger and larger and larger, especially in an e-discovery kind of environment, distributed processing is going to become a fundamentally important concept. As you can see, the benchmarking here really shows that it really produces solid real-world results. We're going to stop here. You can go ahead and pick up in the second video, and again, make sure you watch all these before you get to the lab in any given week.